So we talk about one of the main direction in the physics in 20th century. So the physics actually make a progress in two fields, as you know, the quantum mechanics and the relativity. So I write it the general theory of relativity, because as you know, there are other type of the relativity, which is the special relativity, the first theory proposed by Einstein. So we are talking about the general theory of relativity. So what is the general relativity? It is just a simple extension of the special relativity to special relativity was about the inertial frames. Yeah?
Yes.
The frame which they are moving with the constant speed with respect to each other. We are dealing with the gravity, so gravity means that the acceleration. So it's just extension, simple extension of special relativity to include the gravity. So we wanted to talk about the accelerated frames. So accelerated frames with acceleration A, and in connection to the gravitational field, so G, gravitational acceleration with gravitational field strength. So it's actually special relativity is based on some principle. So you have to accept the principle, or you can relax the principle. If you don't accept the principle, you have another alternative to describe the gravity. So what the Einstein, I wanted to pass the road which Einstein helped the Einstein to relate to the general relativity. So he started by the thinking about the relation between the matter and our intuition and our feeling about the universe. So about I can call it the size. What is the relation between the matter and the size? So matter, we mean by matter, we call it the energy. So we know that because of the special relativity. Because of the special relativity, which we can abbreviate that as a SR, and this is normally we call it GR, we know that the mass is equivalent to the energy according to the famous equations. So I want to tell you that if the quantum mechanics invented before the general relativity, so the understanding between the relation between the matter and the size was more easy. We have one very, very important concept in quantum mechanics which related the size of the system and the measurability to the energy. And this is the Dubois energy equations. You know that the Dubois show that for each material particle, for each matter field, for each moving object, you can define a wavelength for that, and the wavelengths can be measurable when you can measure that, when you can say that a phenomena is wave or is a particle phenomenon. It depends on the size of your measurement instruments. Yes? When you do the optical experiment, you know the light will come. We don't know the light is a particle or the wave, so there is a duality for that. When it touches the double slit experiment, or when you want to do interferometry, so after that you will see that what the pattern will be here. So sometimes you will see the wave behavior of that, and sometimes you just see that small, actually dark points there. So you can say that the photon or the light has this duality, and you know that from quantum mechanics. But because at the time which the general relativity proposed, people not aware very much about the quantum mechanics. The only information about quantum mechanics came from the theory of Planck, from his observation. So actually, as you know, it's a part of the lecture at today's story. So Planck tried to explain the black body radiation, so he proposed the idea of the box of the energy, which any amount of the energy can be divided to the small pack of the energy. So that's one. And that leads to the concept of the quantum. Anyway, because I want to follow the state with the Einstein steps, the Einstein which leads to the general relativity more or less, so we have to not using this simple equivalence between the size or measurability or the filling of the space-time and the energy, but instead of that, I wanted to use the Mach principle. So it's actually a different philosophy. When we feel about the geometry, when we feel about the size, only when the matter exists. So matter give us an idea about the geometry. Okay, there is no proof for that. This is a principle. So I want to say to you that if you are in a place in the world that there is no any matter, I mean, you never can feel the geometry. You never can feel the deformation of the shape of your universe around you. If you see any deformation because of the matter existence. So if there is no matter, so you have not any feeling about the geometry. It looks like very logical. So this is called the Mach principle. So Mach principle is the first key actually for the Einstein to start at the general relativity. So the second key idea was that the equivalence principle. In special relativity, you understood that the phenomena, the motion and the time are relative parameters. So equivalence principle is about doing an experiment in the presence of the gravity and in the presence of the accelerated systems. So you are standing on the ground and you do the experiment which leads to the filling of the gravitational field. So it can be just throw down a ball or the apple from some special distance. So here you have a gravitational field, and you do the same experiment in some accelerated frames, which is accelerating by the acceleration a, and you're standing here and doing the same experiment. The equivalent principles say that basically doing any experiment in the frame in the presence of the gravitational field, results are the same as you do the same experiment in the accelerating frame when there is no gravity. So there is a display which there is no gravity, but you are accelerating with the acceleration a. So if you do the experiment here, experiment means that throw down the ball or apple, so you will get the same results. So that is actually, you can find several simulation of that in the YouTube or the video. So that means that you're standing in the elevator and suddenly the elevator starting to going in free falling. So you will have the free fall. So free falling in empty space, in the vacuum, in empty space. Is empty is also very important things. So free falling observer will feel the same result or feel the same experiment as the person who is feeling the gravitational field. So there is no essential difference between the acceleration and the gravity. But the problem is that accelerated frames like that, they are not inertial actually. Non-inertial frames. Inertial frame, as you know from a special relativity, was the frame which they are uniformly moving actually with the constant velocity. But the non-inertial frames are the frame with acceleration. Is it any other extension of the equivalence principle to the higher orders? I mean, In a spatial relativity, you have the inertial frame. So basically, inertial frame means that you have this frame with the acceleration is the zero, the relative acceleration for them. When the satellite is moving and you are standing on the ground, so one is moving with the constant velocity and one is standing here. So the relative acceleration between them is zero. In general relativity, we are talking about the frame which they are accelerating with respect to each other, but the result of the experiment will be to remain the same for the free-falling observer and for the observer which feel the gravitational field. So do you think there is any other extension of that? You can go to the frame that the accelerating frame receive a second type of the acceleration or something like that? Do you think it's possible? No, velocity is related to the first derivative of the coordinate. So spatial relativity actually is based on the first derivative of the coordinate. Coordinate means generally coordinate in 4-dimensional event. So general relativity is dealing with the acceleration, second derivative. So I want to tell you that general relativity is the last station to extend the idea of spatial relativity, because up to the second order you have the things which the keyword is the causality. You have a causal relation. So if you started in the spatial point with the spatial velocity, finally you will reach the spatial another point. From A to B you can go directly in the causal way. I mean, if you just give me the initial velocity and initial position, I can go to the next point. But it's only for the second order quantities. So if you consider higher order derivative of that, so the causality will be break. So if you wanted to build, forget about what is the gravity, if you wanted to build a theory which remain causal and stable, so the way is that you build your theory from the Lagrangians, which is dealing with the first derivative. I mean, the kinetic energy should come by the first derivative of the coordinate. If you have a Lagrangian which is started by the second derivative, or what does it mean? The kinetic energy of the system be related to the acceleration of the system, so like that. So there is no guarantee that your theory will be causal. So general relativity is not only based on the some principle, so this is also the causal theory. So I mean, in some sense, you can keep it the causality. At least locally, you can have that. And don't forget that the general relativity is also Lorentz invariant locally. Because locally, you can remove, you can ignore, or neglect the effect of the gravity locally. At each point, you feel the gravity, because if you make the comparison between the 2 points in the space-time, if you are looking, if you are standing in the position, so locally, these key points are very important. So general relativity is basically, first is something about the matter and the geometry, so plus geometry, so or the size. The second is that is locally Lorentz invariant also. Just locally Lorentz invariant. So the other things is that is really extension of a spatial relativity. Spatial relativity, as I told you, is just for inertial frame. General relativity gives this possibility to you that you have a invariance for the very general form. So you have a general covariance. I will tell you what is the covariance and contravariant. So this is a general covariant theory actually. I mean, in spatial relativity, you're dealing just by the constant moving observers. So do you remember what was the main equations for that? The equation for the spatial relativity was that the main quantity was that the quantity which we call it that this quantity, c squared, t squared, minus x squared, minus y squared, minus z squared, it was invariant under the certain class of the transformation. We call it Lorentz transformation. And there, the Lorentz transformation had a factor, which we call it Lorentz factor, and the Lorentz factor was a function of the relative velocity between the two frames, and that's all. It was no any other free parameters there. Also, I want to give you a higher order view. This C, if you go and read it something about the Lorentz group, this C is the center of the Lorentz group, central charge of Lorentz group. So, and what about the general relativity? General relativity is something about the happen and measuring in the any frames, not just inertial frames. So I mean that the transformation which will keep some quantity invariant should be more general than the transformation of the Lorentz. Lorentz transformation was like that. You have a vector called x prime, y prime, z prime, and ct prime. So you can always relate that to another old coordinate x through the matrix, or through the matrix, we call it the Lorentz matrix. And if you back to the special relativity, there are special properties for this matrix. So, and that condition supported the idea that the Lorentz transformation made a group. And the Lorentz transformation group is a non-commutative and associative group, so it's called actually a Lie groups. So if you want technically know that what's the Lorentz group. So we are not talking about the Lorentz group so far. So just I want to tell you that instead of the inertial frame and instead of this special, very special type of the transformation, you have to have a very general transformation, which we call it the general coordinate transformation. I mean, x prime can go to any function of the x, the old ones. So about the notations, so this notation I use it for the coordinate and the time all in the 4 dimensions. Sometimes we use the notation of the index. So when we go little more in the topic, so we will introduce the new notation. So the first lecture is just about the main concepts. So very general coordinate transformation would preserve a theory which can describe the gravity as one of the fundamental forces of the natures. I want to tell you one thing about the general relativity. The thing is that general relativity is also a classical theory. So we observe some phenomena in general relativity which they are very, very similar to the phenomena in the quantum mechanics. But general relativity is a classical theory. So it's a classical theory. One more thing is that this is only for the gravity. So this kind of the framework is only for gravity, you know. So gravity, like the other force, like other fields, so it can have some particles to carry the energy. So as you know, the electromagnetic carrier is the photon. So for the graviton, for gravity, it will be the graviton. So you can have the graviton. So such kind of the particles, we call it the gauge fields. Finally, general relativity is a classical gauge theory for gravity. Okay. So a certain type of the transformation, we call it gauge transformation. Because we will repeat this name of the gauge. So I want to tell you that, for example, in electromagnetics, you have the two types of the field, E and the B. So, and for general potential, they are written like that for very special type of the gauge. So, very special kind of conditions about the fields. So, this equation, this function satisfies some equations. Yeah, we know that the Maxwell equation. These equations are invariant on the special type of the change of these two functions, phi and the c. So if you change the phi to the